This is a set of data that I used in a previous video where, in fact, it was the last video, where we found that the mean was equals to the sum of x over n. I was treating this as a population, so this was 32 over 8, which came out to be 4, so I had a mean of 4. And I also worked out the standard deviation as 1.3228. Okay, so I'll link here to the last video where I worked all of this out if you want to see that. But what I want to show you is what happens to my data, or what happens to my variation as I measure it here with the standard deviation. So what happens to this 1.3228 if I make a change to all of my data at once? The sort of thing that would happen if you just add 5 to all of these values, or multiply all of these values by 3, something like that. So you're changing them all in the same way. Now, why, before I get into the math though, why would I bother doing something like that? Well, this sort of thing happens all of the time when you're dealing with sets of numbers. Let's imagine for a moment that these are 8 employees, and this is how much money may be measured in thousands that they make in a month. So somebody makes 4,000, somebody makes 5,000, and so on. Now, I could work out what the average employee's salary is. So 4,000 a month is the average. Some of them make less, 2,000, some of them make more, 6,000, and so on, but the average is 4,000. I could also work out how much variation there is. So most employees are within 1.3 thousand of the average. But what would happen if I was to give everybody like a one-time bonus? So I gave everybody a bonus of 1,000. That would be like taking all of my data and adding 1. So if I did that, if I added 1 to all of my data, what would happen then? So I'm going to create a new value, set of values over here. It's simply just going to be each one of these with 1 added on. So 4 plus 1 is 5, 5 plus 1 is 6, and so on. And then I'm going to go back through and I'm going to find my mean and my standard deviation. And I'm especially going to be highlighting what happens to the standard deviation when you do this sort of a thing to your data. So to make it a little bit quicker, this time when I go through, I'm not going to work things out using the definitional formula. I'm going to use the computational formula, but we'll get to that in a second. Let's start off with the mean. The mean used to be 4. Now the mean is going to be the sum of x over n, and the sum of x is going to change. If you add up these values, 5 plus 6 plus 6 plus 5 plus 5 plus 3 plus 3 plus 7, this time it's not going to come out to be 32 like it did when I worked this out with my original set of data. It's going to come out to be 40. So this is 40. It's divided by 8. The average is equals to 5. Now notice the difference that's occurred here. When I had my original data, my average was 4. Then I added 1 to every one of my data points, and look at what my new average is. It's 1 higher. So if your average is worked out and then you add 1 to all of your data, your average will be, the average of the new data set will be 1 higher. So whatever you do to the data, you do the same thing to the average. What about the standard deviation? What's the standard deviation going to be for my new set of data? So this is my new set of data, and this is my original set of data. Okay, so let's work that one out. To do that, like I said, I was going to not work with my deviations. Instead, I'm going to take an opportunity here to do the computational formula. So the computational formula works like this. The sum of squares is equals to the sum of x squared minus the sum of x in brackets squared over n. I already know what the sum of x is. It's 40. I already know what n is. I need to square that. n is equals to 8. I just need to know the sum of x squared. So I'm going to square my x's. So 5 squared is 25, 6 squared is 36, and so on. You might be wondering why I don't just square 40 again. Isn't the sum of x squared the same as the sum of x squared? Well, not exactly. When you're looking at these two representations of sum of x squared here, you have to keep in mind the order of operations. And I go through this in my videos for the appendices. You have to follow brackets first, then exponents, then division, then multiplication, addition, and subtraction. You have to go through in this order. Now here we have brackets. So what the brackets mean is that you have to work out, ignoring everything else, you have to work out the sum of x first. So the 40 came from adding up these values, x values, not x squared values, but x values first, the sum of x first, ignoring everything else. It's 40, so that's what goes here. Then I can square it. But over here, I have no brackets, so I can forget about that, but I do have an exponent, and I do have summation, which is addition. Exponents come first, so you square things first. That's why I squared them first. Then, after I've dealt with squaring them, my exponent, I can move down to adding them up. So when you add these up, let's see what this is going to be. It comes out to be, the sum of x squared is 214. Okay, so we've got 214 minus 40 squared over 8. And so let's see, what is 40 squared divided by 8? That gives me 200. So 214 minus 200, I've got a sum of squares equals to 14. Now that I've got the sum of squares, I can work out what my variance is, and so I'll need a bit of space for that. So I'll bring that up here. My variance is equals to sum of squares over n, and the sum of squares is 14. N is equals to 8, and this seems kind of familiar. This is exactly what the variance was before. 14 divided by 8 is 1.75, and so of course, if I take the root of the same variance that I got the last time I worked with this data, I mean the same variance as when I had my original set of data. So when we worked with this data the last time, the mean was equals to 4, the standard deviation was equals to 1.3228. Now, when I'm dealing with this set of data, the mean has changed. It went up by 1, but it appears that the standard deviation will not change. I had 1.75 for variance before. I have it again. When I root that, I'm still going to get 1.3228. The standard deviation is unchanged. So the standard deviation is 1.3228. So apparently, when you take all of your values and you add 1, so you do that for all of them, it does affect the mean, but it has no effect on the standard deviation. Now, if you think about it, that should make sense. These employees, if these are employee salaries, these employees have a certain amount of distance or difference between the amounts of money that they're making. So these two employees, for example, they have a $1,000 difference between what they make. So let's say Joe makes $4,000 and Mary makes $5,000. If you give them both a $1,000 bonus, they're still the same distance from each other. And variability, as we measure it, is all about measuring differences between our data points. And the differences between the data points haven't changed at all. As long as we add the same amount to all of our data points, we haven't really done anything to change how spread out the distribution is. So the standard deviation is unaffected by adding to our original data. In fact, if you had done minus 1, it also wouldn't have changed things. If you'd done minus 2 or minus 20 or minus 103, it wouldn't have made any difference. Adding and subtracting makes no difference to variation. What about multiplication? Let's have a look at that one. Let me clear up a little bit of space here. Okay, so let's do, again, just a simple operation on each one of our values here. I'm going to multiply each one of them by 2. So this is going to give me my new set of values, where instead of having a 4 first, I'm going to have an 8. Instead of the 5 times 2 is going to be 10, and so on. And so fill all those out. Okay, so once again, what I'm going to do is I'm going to find the mean and the standard deviation. So let's find the mean and the standard deviation. Okay, so to find the mean, I need to know my sum of x. And so if I do that, if you go through this data set here, let's see, 8 and 10 and 10 and 8, that's going to make 36. And then I'm going to have 48, 64. So 64. This is going to be the sum of x over n. 64 over, we still have 8 values. And so the answer here is 8. So we used to have a mean equals to 4. Then we doubled all of the values, and look, now the mean has also doubled. So whatever you do to the data, the same thing happens to the mean. Last time we saw that we added to the data, we also added the same amount to the mean. Now we're doubling the data, we double the mean. So whatever happens to the data happens to the mean. But last time, we had a standard deviation of 1.3228. We added 1 to all of our values, and that did nothing to the standard deviation. What's going to be the case here? Let's see what goes on. I'm going to do this computational formula once again, so I'm going to do x squared. So 8 squared is 64, 10 squared is 100, 64, 64, 16, 16, and 144. All right, so I have to add these up. That will give me my sum of x squared. And this comes out to be 568. Okay, so that's going to help me get my sum of squares. My sum of squares is the sum of x squared minus the sum of x in brackets squared over n. And I've got 568 minus, in brackets, the sum of x, so that's 64 squared over 8. And so what does this give me? Let's see. Right. Okay, so 64 squared divided by 8 is 512. So I've got 568 minus 512. This gives me 56. So my sum of squares is 56. The sum of squares helps me to find my variance, which is the sum of squares over n. And so that is 56 over 8. That comes out to be 7. Now, 7, I have to take the root of that because I'm looking for my standard deviation. Standard deviation is the root of the variance. And so I need the root of 7. And so I have to take the square root of 7. Let me just see if I can figure that out. And it comes out to be 2.6457. Okay, so this is my new standard deviation. Remember, the old one, the original one, was 1.3228. we doubled our numbers, so we doubled all of the numbers. And what happened to the standard deviation? Well, divide this, or actually, instead of dividing that, let's take the 1.3228 and double it. That comes out to be 2.6456. So except for a little bit of rounding error, the 7 and the 6, I have doubled, or we've witnessed that the standard deviation doubles. So when you double all of your data, you double the standard deviation, which again should make sense. Think about it this way. If these were employee salaries, and Joe has got $4,000 per month and Mary's got $5,000 per month, if you say, I'm going to double both of your salaries, well, now she's making $8,000, he's making $10,000. They used to be $1,000 apart, now they're $2,000 apart. And remember, variation is all about measuring differences between the data. So if you have doubled the size of the differences, you're going to double your measures of variation. So here we're using the standard deviation. We've doubled the standard deviation.